keep the water in gas form. Remember, it takes a tremendous energy input to take the water out of the air to have to turn it into liquid. That's where all the energy gets wasted in that redundant leg on the psychometric chart. So we thought a microporous membrane like this is probably not going to be very much good to us, because as long as it's microporous, air and water are going to just pass through there equally happily, and it's not going to do a separation. It seemed for a while like it was going to be a dead end until we started looking at something called non-porous membranes. And we first said, well, what is a non-porous membrane? If it doesn't have any holes in it, then how does it let anything at all pass through it? And the answer to that is that non-porous membranes are generally made out of polymers. Most plastics are made out of polymers. A polymer is an organic molecule which is very, very long, made of a chain of long molecules. And these molecules tend to get all sort of knotted up together. And they can be manufactured and developed to have a whole variety of properties, strength and toughness and stretchiness and rubberiness, because they are sort of knotted up and they can be stretched out. And they can also be developed to be permeable to certain things and impermeable to others. How friendly they are to certain things, how much they are attracted to them, and how much they let them pass through. This is a very close-up photograph of some of the cells in the lung tissue. And what you see here are some of these groups of molecules and the kind of void space between them, where the substances, the water molecules and other things actually pass in these little cracks and crevices. It's not a very tiny picture, but that's where the transfer is actually happening. This, believe it or not, is a synthetic product right here. This is also made by Gore-Tex, and it's one of their non-porous membranes. It's made out of polymer. And it's not camping out, it's for implanting in the body. It's a synthetic vascular graft. And what this does is controls fluxes within the body. It's grafted to a vein or an artery or some other vessel which contains flows within the body or within the organism. And just by the very nature of the properties, the inherent properties of the material and what it is permeable to and what it is opaque to, it controls the fluxes that happen in the body. So that was very inspirational to us. We thought maybe we're onto something there. It also led us to think quite a lot more about the fundamental properties of materials and how you can exploit those to your advantage. In certain ways, we already do that. It's sort of intuitive to exploit the fundamental strength of timber and the even greater fundamental strength of steel, the inherent compressive strength of concrete in building. But we're always developing ever more sophisticated materials, sort of polymer membranes and Gore-Tex textiles among them. And we were beginning to wonder, how can we understand the fundamental properties of these things even better than we do, and how can we make better application of those properties? Again, it goes back to sort of biology. Current biological thought is evolving to change the way we think about the body and the way we think about medicine as well. Traditional medicine, in a very general sense, has it that the body is a sort of centrally controlled organism where everything operates as a result of signals sent out from a central nervous center. But in fact, we're finding people in medical researchers are finding that's not quite true. A lot of things function in the body simply because that's the way those materials work. The body operates in many ways simply as a result of its fundamental properties of what it's composed of. You cut your finger and it begins to bleed, and eventually that bleeding stops because the blood clots. Well, that's not because they're discovering now. That's not because some central nervous system in the body, the brain or something, sends a signal to the cut in your finger and tells it to clot the blood. It's simply because that's what happens to blood when it comes in contact with oxygen. Similarly, human heart tissue or animal heart tissue, in a way, has a kind of fundamental property in which it twitches, and it will continue to do this in some instances, even if it's excised from the animal. A piece of that tissue is cut off and dropped into a saline solution. It will continue to have this sort of twitching motion for a certain period of time until it finally dies. But again, that tells us that in some ways the circulation system, the heart, doesn't operate on some signal that's being sent from the brain, but it does what it does simply because that's a fundamental property of what it's composed of. So we're very interested in these ideas of fundamental properties and how we can take advantage of them to develop a system which might separate air from water, hence doing part of the job of a traditional air conditioning system in a passive way, simply by taking advantage of the properties of materials. And consequently, if it's passive, it uses less energy. What we're shooting for is to develop a system which will take out the latent load. That means take out the amount of water required in the air to make the building comfortable, and save the energy to do only the sensible cooling part, only to reduce the temperature of the air so that it's comfortable for people. As I said, I don't have a lot of finished work to present to you. All I'm going to be able to show you, I'm afraid, are a few very sketchy sketches, some ideas of what we're beginning to think about. Here, again, is an image of a human lung. It doesn't look like very much when you get it outside the body, but nevertheless, there it is. It has a sort of construction of various lobes, and it's a sort of tissuey substance. It encloses a volume, and you can see, again, this distribution network I've been talking about along the surface. In many ways, it can be said that all the action in the lung happens on the surface rather than in the volume, in the void. And that is, again, what we're thinking about in this passive dehumidification system, is a sort of void of some sort, where all the dehumidification, all the action, as it were, happens on the surface, on the skin. So that we're looking for a skin that actively modulates the energy continuum between the outside conditions and the inside conditions by energy and mass transfer within this skin. I'll show you in another slide what we're thinking about. It involves sort of quite a convoluted passage of the air as it moves through the surface, as it moves from inside to outside and back again. And that's because we need, just like the fish needs with its gills, or the lungs need with their thousands of alveoli that make up the surface of its hemisphere, we need a lot of surface area to get this transfer to happen. One option that we began thinking about before we got onto polymer membranes, in a way, were synthetic traditional materials, porous materials. Any porous material has an affinity for water. That means it will soak up a certain amount of water, and eventually, if the material is thin enough, and depending on what the conditions are on both sides, it will transfer water through it. It will let water permeate from one side to the other. Analogously, it will let energy transfer through it. We all have a sort of intuitive grasp of how good of an insulator a certain material is. Earlier on, I showed you a slide of a tea bag talking about diffusion of mass and diffusion of energy, and I also showed you a slide of a sugar cube soaking up water and also soaking up the attendant heat, the attendant energy in that water. The thing about porous materials is that you get much more of the sugar cube action than you do of the tea bag action. What we were looking at is trying to engineer a facade with a kind of porous material element so that it would soak up the moisture in the air and store it. And gradually, if we could set up conditions favorable on one side and the other side of that porous material, that water and its attendant energy would move through and be removed on the other side of this composite facade. So we were hopeful about this idea. We're still very hopeful about it. I will show you a couple more slides of it and try and show you a few slides farther on still a diagram to explain a little bit better how it's intended to work. But I'll tell you right now that what we're finding is the rate of transfer through a porous facade, this is meant to represent sort of very, very thin terracotta slabs here, is very slow, as is any diffusion process, but through a sort of finite thickness, 1 centimeter or even less than 1 centimeter of a typical material, a traditional material like terracotta, the rate of transfer is so slow that it is almost no good to us. But what we were hoping to do here is to create a double cavity facade where there's a sort of impermeable internal wall, this white space here, and there's a void back behind the terracotta panel. Then there's the terracotta panel and another void in the front of it, enclosed by a sheet of glass. The idea is to create a double ventilated cavity where air would come in one void, let's say the front void here, hot sticky air from the outside, and flow along this surface. If this is the wall of a building, then that gives us the advantage of being able to create a very large surface. So you have a very small amount of air flowing over a very large surface area at a slow rate. If you the idea was to try and entice it to deposit its energy and its moisture into the brick, have that brick soak it up like a sponge. The air would then move on into the inside of the building and be cooled, only the sensible part of the cooling. And then it would be exhausted through the back cavity and out again. And eventually we would hope to get some of the moisture which was stored up in this terracotta to move into that outgoing air stream and be exhausted, taken out of the building. I hope this doesn't seem too confusing, but we, as I said, found that the porous material doesn't work so well, and we've moved on to another option which works similarly, and maybe by explaining that it becomes slightly more clear. Here again are sort of some images of a sort of porous material passively dehumidifying facade which we were working on. Again, very thin terracotta panels, a void behind them and a void in front of them. The void in front of them is covered by glass because we were trying to allow the permeability of glass towards energy. We're trying to use that to our advantage. Glass is very permeable towards energy or radiation. It would allow a lot of the sun's energy to transmit through to terracotta panels, and it's very impermeable to moisture. And so in this way we're, again, trying to control the various fluxes of mass and energy and use them to our advantage. And these panels have a sort of series of bumps, and this is simply an attempt to try and, again, increase the surface area, get more of the material, the diffusing or membranous material into contact with the fluid, the moist air, so that we can get the exchange happening. But this was sort of a dead-end path, not completely dead, but it didn't produce results as encouraging as we were hoping. It's also been, I should just add, quite a challenge for us to find a way of analyzing this. Because this process here does involve a phase change of water. The moisture, which is in the air, moving through this passage and soaking up into the brick. At some point inside that brick, that terracotta, turns into liquid water. And we're all familiar with dampness in the walls of our normal dwellings made of brick. So it involves a phase change simply by the nature of the interaction of water with these materials. And then it involves another phase change again from liquid to vapor when it is exhausted out the backside. That means some energy is involved, some temperature difference happens because when the water that goes into the brick coheres, when the forces of cohesion between those water molecules become so great that it jumps into, they all sort of jump together into a droplet of liquid, they give off a certain amount of energy which tends to heat up the facade. Mathematically, this made quite a difficult situation for us to model at ARIPS. Developing a computer program which models the combined mass and heat transfer of this system. So the development of it has been a little bit slow because of that. But we are now, we've now found a way to do it using computational fluid dynamics, which I'm not going to dwell on at all. But we're working on ways of analyzing this. When we found that sort of traditional porous material, terracotta or wood or something else, wouldn't do what we wanted. In principle, it behaves the way we want it to, and we thought we could get the general action going on, but not at a great enough rate to make any difference. The obvious thing for us to do was to then start looking at non-porous membranes, at polymers, materials that are somewhat similar to those that Gore-Tex uses to make its surgical implants. So we looked for various polymers and tried to engineer various polymers that were very transparent to water vapor, would allow a lot of water vapor to permeate through, and were very non-transparent, very opaque to air. And we set about establishing a similar system where we have two voids, one behind this membrane and one in front of it, both separated by glass. In this case, the membrane is sort of folded up to try and get a higher level of surface area. And again, we try and manipulate the geometry, the spatial configuration of the thing, so that we have a gradient, an incline, if you will, of the energy state. Higher on one side, in one of these voids, the air is both hotter and more humid as it comes in from the outside. And lower on the other side, the air is drier and hopefully has less heat. It's cooler, I beg your pardon, because it's been cooled once it's in the building, and hopefully has less humidity in it, which means that the moisture and the energy both are going to want to sort of go sliding down this incline, this abstract energy incline I'm talking about, from a higher energy state in the outer cavity to a lower energy state in the inner cavity. And then what we've done is use this polymer membrane to put a partition between them, which controls that flux. And what it does, because it's transparent to water vapor and opaque to air, is it lets only the water vapor move through it. A polymer membrane, unlike a porous material like terracotta, is so thin and transparent that the water doesn't stick around and turn into liquid while it's in it. It doesn't get soaked up and stored in the membrane. It's sort of 1 micron thick, and it's transferred immediately through and stripped away to the other side. In some senses, that's very handy because we avoid the phase change altogether. We keep the water always in gaseous phase, and don't have to bother inputting the extra energy to change phases. Here you see a sort of diagram trying to explain how this works. It's reversed to what I just explained. The inside is on the left, outside on the right. Here we have the hot sticky air from the outside coming in. It's at a very high energy level, and as it goes through, it loses some of its moisture to the other airstream. It then comes out and goes through a sensible cooler, or refrigeration cycle. But remember, this refrigerator is only doing sensible cooling now, so it's quite a bit less energy. It then goes in and it makes the people comfortable, the occupants in the building. And as it's exhausted into the other cavity at a lower level on the energy incline. And that's what makes the water vapor flow from one to the other, flowing down that incline. Another detail of this facade, this is just a computer image we developed to try and study how this might be made. A series of sketches looking at various double cavity facades separated by a membrane with various folds in them to increase the surface area. All this talk about minimal energy states is very interesting, and I mentioned at the beginning that it's kind of abstract concept to talk about any system and it trying to reach its minimal energy state. And if you can conceive of any system as a kind of curvy surface, and the energy state of the system as a curvy surface, and the system as a marble which is trying to roll to the lowest point. We can talk about systems of gas and the amount of energy they have in them, which is determined by their temperature and the amount of water or latent energy contained in them. We can also talk about them systems of solids, structural systems trying to reach their lowest energy state. This is often best illustrated with tensile structures. Probably most of you have some familiarity with the work of Fry Otto, who has done a lot of pioneering of tensile structures. And one of the ways he studies those structures is using soap bubbles and soap films. And the reason for that is that a soap film will automatically assume its lowest surface area. It will find the forces that are acting on it, the boundary conditions, which is the wire frame on which you're holding the soap bubble, and the pressures on one side and the pressures on the other side. It, as a fundamental property of its system, will see its lowest energy surface for that. It will try and find the shape that causes it to have the lowest energy to exist. And what that means is that it finds its lowest surface area, its minimum surface area. What we find interesting about that are various other forms in nature which operate that way. Again, we're talking about minimal energy levels of thermodynamic systems of the air that's coming into and out of the building. It's also interesting to talk about the structure itself having a minimal energy level, like a soap bubble, like a tent. This is a spicular nacellarian skeleton. It's a kind of plant that occurs. I don't even know where it occurs in the world. But I think it's quite beautiful, and it's made of rigid elements, sort of sewn together into these things. And what we find very interesting about it is this is a very common form you can get when you're playing around with soap bubbles. If you have a complex enough tetrahedral frame, you can generate this form. And it is this sort of equilateral shape, and all these planes are held together, holding a sort of volume in the center, because all the energies, all these surface energies in each one of these planes are exactly equal. So the tensions are equalizing everything, and it becomes a minimal surface. We find that very interesting. That's about all I can say about it at the moment. As I said, we're still in the process of trying to synthesize these ideas into an architecture, but this is giving us some clues. Again, some sketches on how to make a minimal surface area. Some might remember the blood oxygenator, which was an artificial membrane which had a kind of quilted form to generate a lot of surface area. Again, we're exploring ideas of a kind of quilted skin of a building in which this exchange happens to condition the air as it makes its passage from inside to outside and back again. These are some just sort of purely geometrical studies of the maxillarian skeleton of the soap bubble that I told you about, and how you can form different planes of minimal surface energy, and the kind of by allowing the surface energy of the substance to be the form generator, you sort of default to a certain form, which has a very definite reason for its existence. The reason is that it's minimal energy. It's an idea about letting the system determine what happens. Again, controlling the fluxes and flows of the system as it moves from a higher energy state to a lower energy state, and turning that to your advantage. Similar to the way in which we're trying to control the flux of the incoming air and the outgoing air, so that the energy exchange moves towards its lowest energy state, and that works for us to create a more comfortable environment, an environment that's less humid inside. We're interested in developing in tandem with that a kind of form which finds its lowest energy state, a structure which is allowed to find its lowest energy state, and that's what helps us to determine the form. We don't know exactly how that's going to take place yet, but that's what we're working towards. And these are just a sort of series of sketches of some ideas, various things that are going on in discussion with other engineers at Breshears. And finally, I know it might seem like a slightly abrupt way to end, but as I said, it's a work in progress, and there isn't an ending yet. This is what we're doing, trying to bear in mind this different frame of reference, this different way of conceiving of things that I spent quite a while talking about at the beginning. The fact that the atmosphere is one fluid and energy continuum, and that we exist in a fluid and energy continuum, and there's no getting away from that. That no matter how hard we try, we're not going to create absolute step changes in that continuum from a hot and sweaty exterior immediately into a perfectly cool and comfortable interior environment. The best we can do is to try and modulate the fluxes of air, moisture, and energy as they move into and out of the building, to try and create depressions, create those low spots in the surface of the energy state, so that the model of the energy system can roll towards them. I hope it doesn't sound to you like I'm battling on in abstract gibberish, but it remains a bit abstract in terms, it remains in abstract terms so far. So I'll just leave you with a couple of images to contemplate. One, a building which is basically an enclosure, just formed primarily of a membrane. So again, this is going to be a low energy structure, a low surface energy structure, beg your pardon. Its form is determined as a minimal surface area of the membrane based on the boundary conditions, how the sort of plan, the edge form of this membrane, and these sort of rigid surfaces, spicular skeletons. The membrane is then left to find its own minimal surface area form in between that. And fluid and energy, and how the surface tension of a fluid causes it to bond together to cohere in various ways, and find its minimal energy level when it's disturbed, when a splash occurs, when something happens within this fluid continuum to interrupt its continuity, its perfectly level surface. The energies and masses move around in various ways, in various very interesting ways, determined by the thermodynamic laws and fluid mechanic laws of lowest energy. So I have to leave you with those two images, as I said. And I realize this has been a very disjointed lecture. It's probably somewhat symptomatic and symbolic of the kind of non-linear way in which we're going about this, and the sort of digressive thinking we're trying to embody in synthesizing some of these ideas, some of these concepts which are inherent in nature and inherent in biomedical technology, to develop an architecture. We don't know where it's going yet. We know what we'd like to do, which is to create a passive deconforming system. And I would very much welcome it if whatsoever. If they'd like to make them, either here in front of everyone or just up to me personally afterwards, because at this stage of the development, any kind of input is useful to us. So, if anybody would like to say anything, please do.
Well, perhaps if anyone wants to speak to you afterwards, they will. In the meantime, thank you very much. Same time, same place next week. Tim with Technology and Peter Ross. If you could try and get here for 11, it's a real pain in the ass for people to stop going out every year. So thanks for those people.